Okay, let's get started. My name is Bob Westervelt, and I'll be the host for this series of the Quantum Materials and Devices seminars. Primarily, this acts like an open seminar series in this topic, and we have really a great group of people signed up. A few from our Center for Integrated Quantum Materials here, MIT and Howard. But then also we're bringing in about half of the speakers from outside, like Jim Owens coming up from Columbia and other people. There's a schedule that's posted both on the website and on various places, like outside my office. So it's a great series, and you're free to just come here and have the free cookies, coffees, and great talks. But it's also a nice way to look at this new area of science as a course. And so we have a pass-fail course it's called Engineering Sciences 294. And you can enroll for this course just the same way as you would enroll on the web, I guess, these days, for any course. And there's no homework and no final exam, but we do require something, is that you actually attend the lectures, and so, or at least most all of them, in reasonable excuses are of course accepted. But we need the people taking the course to actually put your name down each one that you've attended. And so I'll leave this here. Today we have Philip Kim, who happily is now at Harvard, to talk about atomic layer materials. And Philip is one of the first and best people to look in this area. It turns out the band structure for graphene was correctly solved before I was born, and I'm not young anymore. But nobody had the wit to actually. That's, oh my God. And, but nobody thought you could actually take a piece of Scotch tape and then pull and go like this and actually end up with graphene until fairly recently. And Kim's group has been had a big impact both in the science of understanding that you can see things like quantum Hall effect at room temperature and these small structures. And he's also one of the best device makers that I know, although people don't usually phrase it that way, but they find out how you can make really elaborate structures for various tricks and diamonds. And so he's going to give us an overview of that.
Great. Thank you. Thank you, Bob. Right. It's my pleasure to be here again. Seems like every year or every half year that I'm supposed to be here and just give us some overview. So today is a little bit different though. So let me see. Okay. So today, basically, I'm here as this team leader or thrust leader of the CIQM. So CIQM recently reforms in terms of the structures research formats, and this stacking atomic layers into the new materials. In fact, this title of the team that consists of the many PIs in the CIQM, Harvard, MIT, and Howard universities. And then I'm going to just to give you an overview that what kind of project we are interested in, what are the goals that we are pushing now. So you will see, in a sense, that kind of many subjects will go through that ought to be superficials. But nevertheless, I hope that you get the sense that some of this exciting project and kind of share the goals that as a center we have. So let me start with introducing the PIs. That in this team, there are basically 10 PIs that belong to this team, and then few others that associate members in the teams. And you will see that a lot of projects we are just pushing is not only one PI's efforts, but the many PIs, 2 or 3, even sometimes even more than 4 PI's efforts. I'm going to just kind of highlight the PI's contribution as much as possible, but in truth, I know that it's not the PI who actually do work. I know that many familiar faces here that it's you guys who work, and then I'm sure that if there's a question arise that something that I'm not familiar, I will just pinpoint that one of you just can answer that the question. So kind of this is an exciting part. The team consists of the probably about equal number of the PIs from Harvard and MIT and some of the Harvard University members. Okay, so let me start with atomic layer system. I think this has been kind of discussed many times. That so-called the rise of 2D van der Waals systems actually is a main topic of this theme that we have. It probably started out the graphene about 12, 13 years ago or something like that. But then soon after, like the graphene, there are other 2D materials that one can extract from van der Waals system, like the boron nitride, transition metal dichalcogenide, some cases high temperature superconductors such as BISCO. And there are a lot of systems that contains this van der Waals interaction between the layer, which allows us in principle that extract this material down to one monoatomic layer. Soon that it's been also figured out that it's not only they do exist, but they can exhibit quite interesting electronic properties or magnetic properties and other properties, right? Just looking at this TMDC alone or TMDC kind of graphene on only these three kinds, you can easily find out that insulator semimetals, superconductor, charge-dense waves, P-type or N-type semiconductors and so on, and some of them becomes even magnetic. So there are a lot of different type of this, the physical properties exciting. But on the top of that, you can in principle just put them together and restructure to the just functional heterostructures. So basically rebuild this the system into the stacks of the different functionalities and ask that what kind of physical properties there be. So that's basically one of the real excitement that we have by combining this system, that we can just get the new functionality and new physical properties and so on. It's not only the PowerPoint, it's not only just kind of on in this conceptual level. Already in the few years back, the collaboration I had at Columbia or other places started to demonstrate that simple techniques such as just kind of using the Scotch tape or a little bit more elaborate method using some polymer to extract the crystals, breaking down the crystal down to single monoatomic layer, and you can just reconstruct by just stacking them together in careful manner. And demonstrate that with the right condition, you can get the extremely clean interface between them. So that's quite exciting news. So you can, in principle, build up this quasi-3-dimensional structures. Not only you can just build a stack, there has been some method developed that you can just contact individual layer, individual atomic layer, however they are closely spaced, such that you can make the lateral and vertical contacts to turn into the electronic device. In a sense, the heterostructures, atomic scale heterostructure is pretty much resembles some of the semiconductor heterostructures people can make with MB techniques, right? One thing that we can do better is, of course, you can just really push into the quantum limit. Quantum limit, in a sense, really atomic scale. You cannot go even thinner than that because it's 1 atom thick, right? And with the extremely sharp interface. But on the top of that, another advantage we have perhaps is that in principle we can make the contact on each individual atomic layer, which has been extremely difficult for the semiconductor heterostructures. There has been some efforts that you can make the contact on two of these bilayer heterostructures in the quantum well, but that's about it. I think even that technology takes a long time to develop, but compared with that, this has a kind of clear advantage that we demonstrated. And of course, in such a clean interface with the highly efficient contact one can make, device often turns out extremely high mobilities, extremely good quality, such that you can study a lot of interesting quantum transport phenomena. Not only you can just build this by hand, also there has been some efforts, indeed quite a bit of efforts happens in the material science or chemistry side. For example, here I'm showing that one of the data that I just kind of extracted from Jin Kong's group, MIT, one of their team members. They can grow this the material by the CVD with various different precursors they apply. So they can grow the graphene, boron nitride in certain cases, moly disulfide, tungsten diselenide, and those kind of things. Not only down to just kind of monoatomic layer, but also they have been demonstrating now that you can make this lateral heterostructures or vertical heterostructures by just controlling the growth conditions. So growth is quickly taking over now. Not only you can just build by hand, even the larger scale or bit more controllable and cleaner interface growth is it's being developed in this the material growth communities. And that's another quite kind of important note I want to make. As I mentioned, that interface we can make out of this the two-dimensional system is quite diverse, right? Even just have the two systems together, you just put them together. If you have n type of the material, then quickly you can get n square of this the interfacial choices, n square divided by 2 interfacial choices. And if you just choose different kind of electronic properties, such as semiconductor, superconductor meeting with a ferromagnet, for example, we don't know what this interface will look like a priori, right? So that's kind of the general excitement and theme that we have. So in our team, basically, we lay out some of the project. Of course, there are many, many exciting projects, but we actually carefully chose some of the projects that meet with our expertise. And probably our center, CIQM as a center, may have the advantage over the others. And these are some of the carefully chosen the topics. I'm not going to go kind of read it through because I will just step through them one by one and show just kind of briefly. But as you see here, that the project actually spans not only electronic properties, not only in the physics, but also it contains some of the chemistry aspect, some of this metrology developed aspect, some of the optical optoelectronic processes, or kind of some of the electronic device aspect. So it spans kind of really interdisciplinary cuts of the kind of various different project, subject. I think that's kind of another exciting part of this theme. All right, so in the rest of the time, probably I'm going to just kind of step through this different project and who are the PIs got involved and what has been done and what we are planning to do. So that's basically the theme, the plan that I have. But obviously, I'm happy to just stop any point. And if you have any questions, or even better, if you want to kind of discuss about there's even better project we can just try out. We can always turn this as a kind of exciting discussion stage, right? Okay, so let me start with the first project. So first project is related with this commensuration and incommensurations between the van der Waals interface. So even if you have the same van der Waals or the two fixed van der Waals materials, say graphene and boron nitride, graphene to graphene, moly disulfide, and any things, right? I mentioned that by just putting them together, you get the interface, that interfacial properties interesting that may share or may not share or competing that electronic property of each constituent object of atomic layer. But there's one more thing that we can control. That's basically the angle between them than when I just put them together. Remember, these are all the atomic scale objects where that there's certain degree, certain kind of degree of freedom that you can choose by crystallographic axis. So by just kind of carefully choosing the angle of the stacking, often then you get the very interesting and different type of properties. Let me show you the really kind of well-established example at this point. So graphene and boron nitride. I mentioned that putting graphene into the boron nitride serves as a great substrate, great dielectrics. You get the huge enhancement of mobility in the graphene. But there is one more thing. By just choosing careful angle between the graphene and boron nitride, if you just look at the atomic scale detail, you get the rather complicated structures. However, if you just average out of the detail of the atomic structures, in the large coarse grain structures, there's some modulation, large scale modulation, what you call the Moire pattern. Basically, this is a general things up here. When you have the two similar, it doesn't have to, or either same, identical, or very similar, the structure of the lattice, you just put them together, they start kind of create some sort of the visual interference, what we call the Moire. In fact, the visual recognition is Moire, or get rid of the Moire is really important issues, right? But that's basically, we are getting these atomic scale Moire patterns, which you can interpret it as the relatively large scale, usually about nanometers, 10 nanometer length scale of the modulation. So this is a way that you can engineer in some of the electrostatic potential modulation into the system. It turns out the graphene on the top of the boron nitride, this is quite often appears in the sense, this type of the patterns appears at a lot of the STM data and a lot of the structure, the studies indicating that Moire formation is quite ubiquitous. And not only that, if you just have the Moire, because of this the modulation of the potentials, under the magnetic field, basically there are two competing the length scale that create the so-called the Hofstadter's butterfly problem. That problem has been solved theoretically many years ago. Basically, there are two competing the periodicity. One comes from the electric periodic potentials, and the other comes from magnetic lengths, which actually give some kind of the cyclotron orbits, another periodicity. Competition of these two things basically create this interesting quantum transport phenomena. In a sense, basically you have the two topologically the protected number. One is basically Landau level filling fractions. The other one is band filling coming from this Moire. And between these two interference, basically you get the quite intriguing the quantum features. Basically, that's what Douglas Hofscher's predicted in already 1976 of his the seminal paper, now called the Hofscher's butterfly. What happened is basically the energy structure here, energy level structure here under the magnetic field is basically fractionalized, more precisely fractalized. Because of this fractalized energy spectrums, once you apply the magnetic field and look at the whole effect, basically, whole effect should be described by the two integer number rather than one integer numbers, which actually has been experimentally observed a few years ago. Both at Harvard, back then I was at Columbia, and MIT and Manchester. It's about the same time people start to see that this is not only just existing the theorist of the paper, but actually one can engineer that by just kind of carefully put the graphene onto the boron nitride, creating these structures and get all this the beautiful the fractal quantum Moire effect can form. So this is a good example that indeed, just by simply just adjusting this, the angles, you get kind of interesting structures. Quite recently, this was taken one step further. What if that instead of I have the graphene to boron nitride, what if simply just put the two graphene together, but not in the Werner stacking as usual, but some twisting angle. So that experiment was done by Pablo at MIT. And then you will see that there is a really nice theoretical collaborations done with the Kakshiras. The method actually they developed is quite a cute method, cute method. So they basically use so-called the tear and the rotation method. Basically, to control this kind of angle really carefully, you need to know the crystallographic axis very well. So what Pablo's group did is they just kind of pick up the graphene, only part of that, and by picking up, they tear it off, and because of the remaining part and the teared part has the same lattice orientation, by just tearing off, and they just kind of twist it with whatever angle do you want to do, and just you pick it up, and just create this the graphene heterostructures with some known twist angle, right? So that's what they did. And then one day actually make the device out of it with the boron nitride encapsulations and measure it. That's suddenly found kind of quite intriguing things. Basically, so-called the Dirac peaks, and there's side peaks, usually comes from this Moire patterns or Moire superlattice, and they find that this Moire superlattice peak is much more insulating than Dirac point. In fact, it is if you just measure the gap out of this activation energy, they have a sizable gap, something like the 50 millielectric volt or something, right? And this is very unusual, right? Because you have the highly conducting one system, highly conducting another system, basically couple them together, somehow you get the insulator in sometimes, right? So there are some things going on. It cannot be explained simply in terms of the Moire that I just kind of throw in there. There's much more detail of the consideration has been done. So what has been done? Okay, so this is a Kakshiras group's result. Basically, they just kind of try to compute the atomic scale of the band structures. And of course, there are the twisted, the Brilliant-Jones, but then they have to think about how they actually hybridize together to form the band structures. This is non-trivial techniques, by the way, because there's no guarantee that these two lattices commensurate each other. So the group actually developed how to deal with this incommensuration issue. But at the end of the day, they see actually that hybrid band structures, and more interestingly, that actually shows up the gap at this kind of the degenerate points, right? So gap opens up because of that hybridization gap. They worked it out. But actually, the step going further, because now you know the band structures, you know that once you apply the magnetic field, how they develop the Landau levels. And one way you can just check that is basically measuring, again, that under the magnetic field, measure this Landau fan diagram. That's what Pablo's group did. And they see that this main fans and side fans, there are a lot of interesting quantum Moire effect appears. And it's rather complicated quantum Moire effect. What I surprised when I see this work is when just kind of looking at these band structures and compute this, what is the expected quantum Hall, they beautifully match with the experiments in all these exclusive details. Tells us that the theory and experiment goes really, really going together very well, right? So this is a good example that when we engineer these structures, we can also see the interesting physics, but also it actually leads into the new descriptions, a new theoretical need, how to describe these commensuration and incommensuration issues. But I would say that this is kind of beginning. The reason that I'm saying the beginning is that here, that one thing that you consider is the two lattices, just put them together, and you just kind of consider the no distortion of the lattice. However, we know that that's not really what nature does. In fact, there has been some studies that say graphene, even just kind of Bonner stack bilayer graphene, if you just look at the Bonner stack bilayer graphene very carefully using the TEM, often you find that there is a so-called structural soliton. In other words, the ABBA Bonner stacking changes to the BA Bonner stacking at some point with the sum of the so-called structural soliton structures there. And there has been the TEM studies that demonstrate how one can find those domain boundary. And in this domain boundary, it's a very interesting domain boundary because it's not only structural soliton, but if you look at the electronic structure, it contains some of the chiral 1D gravity states that passing through these domain structures. What is interesting thing is that there has been some of these techniques that developed using the TEM, dark field imaging techniques with the tilted the beam line. You can find out where's the domains and where's the domain, the boundaries actually runs through in this type of the device. Quite recently, in collaboration with David Bell here, that my group actually started to look at this the bilayer. You just kind of put them together like the very similar way that Pablo did to create this bilayer graphene. And using the TEM, we start to find out, well, there are a lot of domain structures, forms, and following through them more or less than the Moire like the structures. What is important part is that this is indicating that the lattice itself start kind of distort or they're reconstructed. I mean, that's kind of clearly imaginable, right? Because this lattice is not the rigid structures. When you just put them together to form the Moire patterns, when you just have this no risk, the deformation of each of the lattice, yes, they do form the Moire patterns. And often, most of the time, they are incommensurated. But what nature wants to do is once they actually make the sum of the commensuration, they gain the energies. So most of the domain, they want to form this, the commensuration structures, and most of the incommensuration part will just reside into this domain boundary where that you can consider as a discommensuration line or structure soliton, right? In other words, instead of just kind of hunting for this structure soliton in the bilayer graphene randomly, in principle, by just kind of rotating this type of the lattice, one can actually create this, the domain structures with the structure soliton. And moreover, you can actually study their structure informations out of this, the TM. Or more importantly, you can just combine this with the electrical transport and probably study about that how this type of the deformations or reconstructions affect the electronic structures. It could be quite interesting because this domain network can be explained in terms of basically network of the 1D chiral mode, transport mode that's kind of connected together, right? We don't have the real data here, but this is kind of proposal. So that can be quite interesting things. But that's only also the beginning. It doesn't have to be on the graphene, right? It can be any other 2D materials. Indeed, quite recent, the work start to show that if you just put the two different systems, like say moly disulfide and moly disulfide, put them together with a small twisting angle, very similar way, or actually in this case, a large twisting angle because you have to break the lattice symmetry, then you can create those kind of domains and the domains wall. We don't know what is this domain wall should look like in terms of electronic properties, and that's why the team and both helpers that the efforts comes in. Just think about all this material has a very strong spin-orbit coupling. When you have this structure soliton and the stacking, two-layer stacking, what kind of electronic properties they may have? And these are completely open questions, but now technically available for this kind of system. So that's basically the idea of this twintronics. Basically, even with the same materials or the known material, we know that individual lattice, when you just put them together and put some of the angles, and especially when you just create some of the incommensurations that try to turn into the commensurations, that at the verge of this incommensuration, they're basically rising the very interesting new physics there. It's like the Hofstadter's butterfly and expand it without magnetic field. Question? Yeah. As long as this is a large area, it seems like reasonably stable. We don't know about the moly disulfide, but at least in the graphene, the structure soliton they create, it's reasonably stable. Something like you need kind of 1,000 degrees start kind of really move this domain walls around. Maybe it's pin in some things, but at this point, experimentally, it's reasonably stable. Right. Yeah.
What was the parameter to like measure the commensuration in commensuration?
There are many parameters. Of course, the angle, the overall angle that I just put there, that will give you some sort of boundary conditions. But how they actually deform, what is domain size, I think that's it depends on the all things that like the elastic constant, elastic modulus, and all of these things, right? So it's a very difficult. And what is the shape of the domains and those kind of things also not well known. I think there are some theoretical the considerations. Actually, people start to kind of put an effort to understand this kind of domain formations. All right. So next topic that I want to kind of briefly mention is chemical modifications. So individual lattice itself is interesting, but also this is a two-dimensional lattice, two-dimensional materials, which means it actually has an exposed surface. In fact, it's actually interesting because two-dimensional system surface is a bulk, right? So there have been a lot of these chemical techniques that developed that how to modify the surface by chemistry, by adsorption, by just giving some of the chemisoption or physics and those kind of methods, we know that how to do the surface chemistry with. But in some sense, in the 2D materials, surface chemistry itself becomes a bulk chemistry. And there are a lot of the interesting tweaks one can make. Here is some of this list, probably part of the list, basically submitted by the excellent chemist and material scientists in our team, Tina Bro and Jin Kong. The growth is also an important part. The modifications, chemical modification is another important part. A lot of time that we want to develop the transferring method. This is another very practically important because to make the stacks, you want to kind of put the right amount of polymers, the right kind of polymers, and you want to get rid of polymers to get the really clean interface. These are all the mundane projects, but in some sense, every step is very important to create a really high quality sample, right? And also how to characterize this type of sample. So there are a lot of the lists that we are also collaborating. Many of the people that are working on this field are collaborating because a high quality of sample is very important. But another interesting times in terms of this, the modification is intercalations. And that, let me just kind of mention that a little bit detail. Intercalation is a particular the chemical process one can induce when you have the layered system. In fact, this is widely used. Everybody has this intercalating device in your pockets right now. All this lithium-ion battery, basically there is always the intercalation and de-intercalation processing is happening at the heart of the battery operation. In fact, how to create a better quality of intercalation is extremely important for the battery industry. And this is probably that some of this electrochemical process we usually physicists do not care too much. But here it's already having this crystal materials of the 2D layer very thin. There are many things one can also contribute. For example, you can start with a really single crystal and see how the intercalation process is happening by just kind of really observed it under the optical microscope. Here is a good example, right? So here's graphite. I think it's a few layer graphene, contact with the electrode, put everything in the electrochemical cells and applying the voltage and start the intercalation is happening. It's not what's seen here. It starts to intercalate from here. Center is growing out and color changes. And this all kind of things can be done in a control way. Moreover, you can actually just looking at these structures, the Raman structures or the Carla structures, you can tell that what is so-called the stage of the intercalation, how this, the intercalants actually get into this layer. This has been better done in the graphene for now, but in principle, this can also can be done in many different layered system, in few layered system. Now, important angle that we can just present here is the controllability and characterizations. How we can do that? Well, we can build up the device. Here is a good example. So here is a device that made of the graphene, or it can be one or few layer graphene, encapsulated and only opens these edges that ion can intercalate in. So we have the kind of well-defined path that it can get in. And during the intercalations on this small electrochemical cell, we can monitor the optical signal, such as a Raman signal. But at the same time, if you just do it well, you can actually monitor also whole voltage under the magnetic field. And that immediately tells you how much carriers you just plug in, how many the lithium, for example, get intercalated in. This is not the science fiction. It has been done in my groups and in collaboration with the various peoples. Especially theory collaboration is important here. again, Tim's and Steve's the involvement is very important because the data can tell you that what can be intercalated, what can be not. So we can actually choose on these different intercalants. And we start to see that both the Raman data and the whole data, we know that what is intercalation stage and how to quantitatively analyze this type of the data. And once you learn about these things in the graphene, say lithium, which is the model system, one can also expand it into the other layer of the system. For example, black phosphorus is another interesting system, which actually has a very interesting ionic potentials that can be intercalated with various different systems. So we start kind of make the black phosphorus device with encapsulated, with exposed edges, and try to drive this intercalants by just kind of control ways. So this is another kind of control chemistry one can induce with the various type of the collaboration going through. Right. Okay, so move on to the other topics. Now, I just told you that we can assemble in the different way or just modify, but also we want to characterize, and then I already present that the transport characterization is a really good tool. But transport characterization is only a limited tool, I would say, because it's average over the entire sample. Maybe one thing that you want to do is, I want to get to some of the local informations, right? How can we do that? Or better, that I'm interested in more of this, rather than transport, some thermodynamic quantity. Is there a way that we can just do that? Well, the problem of these typical 2D materials that we just dealing with now is rather small, right? Either you create by just stacking by hand, or you just grow. Right now, the high quality sample that we can see that this quantum transport, they are usually relatively small, something like the micron size, 10 micron size at the best, right? So the tool that we can just kind of deliver to understand or to study them are rather limited. Here's kind of the tools that this center has expertise I'm going to show you other than just a transport. One is our dear the leaders or the directors of the tool that the Westerveld group is a real expert to have on this scanning gate microscope. Has been developed over the many years now and worked it beautifully onto the other two-dimensional electron gas that formed in the gallium arsenide. Now, this 2D material is basically the kind of new opportunity for the scanning gate microscopy in some sense, because compared with the other 2D or semiconductor heterostructure where this conducting layer is inherently buried underneath the surface, in principle 2D device, you can expose your channel onto the surface such that you can actually address with the scanning probe rather easily and can get the, in principle, extremely high resolutions. Already very preliminary study we just did. We just kind of provide this the graphene device encapsulated in boron nitride, close the ballistic conductions in the device, and just combining with the scanning gate probe, one can also tell us that interesting things. For example, one way you can probe that this device is working as a ballistic transport is simply applying the magnetic field. Applying the magnetic field, you can actually tweak this direction of this electron by just the Lorentz force. Now bring the tip onto the part where electron path and just scatter off this electron that kind of going through ballistically under the magnetic field. You can just modulate the current into the device. Basically, that's kind of interesting schemes one can do. Indeed, data shows that in this very same device, just send the current from one to there and just so send the current from here to there and just using the this tip scans over and monitor how the resistance got changes. They start to see that indeed there is an enhancement of the current. There is a depression of the current. Enhancement of current and the depression of current actually alternating appears in these patterns. And the way that one can understand this one is, of course, it depends on the tip positions. Some path that you scatter off the electrons such that you depress the current flow. On some part, basically the tip-induced scattering actually enhance the current on the path. A detail of this analysis need to be done with the theoretically, which was done by the Rick Haller, and just kind of demonstrate that indeed we can understand these patterns just using the tip-induced scatterings, enhanced or depression of scatterings in the system. Not only that, by changing the magnetic field and the density, you can actually monitor that how this current path will changes as a function of both magnetic field and the density. And as you see here, the theory and the experiment goes really well one-to-one, again indicating that this is a really useful tool to understand the electron path into the system, right? But I would say also this is just beginning. Now you can just expand this other 2D materials. Graphene is a good system that you can make the ballistic device, but also this system can be applicable for the other 2D materials. How about the boron nitride? How about the molybdenum disulfide, semiconductors, right? Now, semiconductor, the molybdenum disulfide, unfortunately, material quality is at this point not as good as graphene. So if you look at the mobility, at the low temperature mobility is at the most something like the 10,000 at that level, right? So probably almost 2 or 3 of those magnitude inferior than graphene. Relatively short mean free path, a lot of the trap densities in there, but there's one great things onto this molybdenum disulfide compared with the graphene. They do have the gap and sizable gap, and that can be utilized to deplete the system and to form some of the lateral quantum structures by the gating. So that's kind of another advantage. And also, because of these depletions, when you just put down this scanning probe, the sensitivity can be enhanced quite a bit because the tip can deplete the underneath such that you can create the relatively strong scatters compared with the graphene case. Very preliminary data at this point, with Bob's permission, I can just present, or Saga's permission. They start to see that indeed this type of whole bar device that biasing the current between them with the scanning gate, when the tip is on the right path that blocking the most of the current, they start to see the current modulation, and we know that it's actually doing this right job. More intriguing part is if you just look at this narrow neck of the lead, you do see the more localized structures and possibly this charging effect, as you see that there's the concentric circles usually coming from this Coulomb charging effect appearing, indicating that indeed this scanning probe microscope can be sensitively detect the defect in the system or charging effect in the systems and so on. So this is just the beginning. It's really preliminary data, but it's very promising. Now the next step that of course one can do is in the molybdenum disulfide, one can combine these techniques with various different type of the lateral quantum structure I just mentioned, because we can make the quantum structures by depletion. For example, this is kind of some of the recent work going in my group. You can just put the lateral the gates in there on the top, on the below of this molybdenum disulfide, the stacks. So you can form the energizing this gate underneath that you can form the quantum dots that connected with another lead, right? Controlling this gate voltages, you can just kind of get this the couplings between the lead to the dot, or you can make the quantum point contact. This basically is Bob's probably old subject, kind of quite familiar with, right? But this can be done in the 2D system, 2D semiconductor. That's actually good things, interesting things. What is new? Now, this molybdenum disulfide or this the TMDC semiconductor, they have very strong spin-orbit coupling. So there's a valley and spin lockings there. Means that if somehow you control the spin, or if you somehow control the valley, there is a good chance you can actually change the current path or the spin path. Or current path depends on the spin states or vice versa, right? So this type of the new things is basically new flavor that we can bring in tied with this scanning probe microscopy. So while the scanning probe microscopy give you that some of the sense, that really local sense, I just told you that another thing that one can probably wants to do is thermodynamic measurement, because that's a really robust quantity and sometimes a more direct quantity, direct physical quantity you want to study. Unfortunately, all the transport measurement I just present is somehow connected with a thermodynamic quantity, but it itself is not the thermodynamic quantity. But here is one thing that one can be done. This is expertise of the Ray Ashuri's group, MIT. So Ashuri's group has been developed this way to detect this quantum capacitance in small-scale device. This is a rather difficult technique, I would say, because it requires many different things. Because you need to access a quantum capacitance, basically the kind of quantum density of state type of the information, you have to go to the low temperature. And often you need to apply the strong magnetic field to just make this enough features in there, like the quantum states, right? And to do this capacitance measurement, because you are dealing with a really small capacitance, you have to drive in high frequencies to get the enough signal. So basically, you have the combination of the low temperature, high magnetic field, and high frequencies. This is not the easy techniques, I would say. Now, over the years, they actually have developed, and here's a good example. So they have these HEMT structures that are dealing with all the high frequency amplifications. They deliberately put this HEMT the perpendicular to the magnetic field direction, such that Hempel characteristic does not degrade it. And now, in combination with the Pavlov's group at MIT, they know that how to fabricate this the 2D materials, the 2D system. For example, in this particular case, bilayer graphene that between the top and bottom gates, and this can measure the quantum capacitance of this bilayer graphene in this type of setup. Now, interesting part here is in the bilayer graphene, you can just put the top and bottom contacts, such as in this way, right? So, and the graphene is also connected, right? And let's say that when you just apply this, the voltages and just try to measure the capacitance, if the graphene were the perfect conductor, basically this is two capacitors in series, nothing special will happen. However, meaning the quantum capacitance means that basically it's not the perfect the metallic system, and there are finite effect, a finite density of state effect appears as the quantum capacitance, meaning that when you charge this type of the capacitor, there's always a field penetrated through this graphene. And that information, penetration field information, is essential information so you can get about this, the quantum capacitance of the system. Why the quantum capacitance of the system is important? That contains information of the density of state, but not the single particle density of state, but many body density of state. It's thermodynamic quantity. One can actually tell all this intrinsic phase of the system. What they did is they just measured this quantum capacitance as a function of this both bias in the symmetric way and asymmetric way in the gate voltage, and they can define so-called the symmetric capacitance or symmetric capacitance as a function of the density as well as the magnetic field. And they start to see that, try to look at how the symmetric part and asymmetric part of capacitance changes. And it turns out it contains a really useful information. Tells about what is their pseudo spin and spin and layered spin, so-called the SU8, the quantum Hall ferromagnet states in the bilayer graphene in the 0 Landau level look alike, and how their phase transition look alike. They can just completely map it out, this type of complicated phase diagram using this quantum capacitance measurement. It's beautifully done and really shows that the strength of the quantum capacitance measurement. Of course, coming up, the next one is we don't have to confine ourselves onto the graphene again, right? It can be done in any other two-dimensional system, right? It can be done even just some sort of 2D superconductors in certain limits with the vortex. And there are many things one can imagine that to measure this quantum capacitance components, to understand this many-body correlation into the 2D system in strong quantum limits. So that's another directions we can push it through. Okay. Question? Okay, so I'm probably about the right time. So next topic that I want to discuss briefly is a somewhat kind of different direction. It's the optical and optoelectronic process. The graphene, I would say that in past 10, 15 years of the graphene research, it was heavily dominated by the guy like me just doing the transport measurement, because it doesn't have the gap, and when you shine the light only creates the second order effects, kind of, right? And most of the basically transport is basically king of this graphene study. However, when it comes with the semiconducting TMDC, the role of the transport and the role of the optical spectroscopy more or less reversed, because there's a gap. And when you shine the light, you get a lot of interesting things comes around. You have the Ramans, strong Raman signals, strong the photoluminescence signal. Transport always suffered how to make the good contact onto this semiconductor, and that has been kind of quite intriguing observation. I briefly mentioned that many of the TMDC, they have the gap, as well as due to the strong spin-orbit coupling, there are spin and orbits lockings there. So good example is the TMDCs. Say graphene no gap, bilayer graphene no gap, but once you apply the magnetic electric field, they open up the gap. Boron nitride, they have the gap because now you break the inversion symmetry of the crystals. Now TMDCs, not only you just break the inversion symmetries, but there is a strong spin-orbit couplings. Basically, that will give you the gap opening as well as the band splitting, basically spin splitting, spin polarized gaps, band splitting, especially in the valence band. So you expect to see that a lot of this optical process, which actually sensitive the spin of the system. Indeed, there have been a lot of the studies out there now shine the light with the circular polarized light, and they're the response, optical response can be quite different. And often the people now just even talk about the electronics somehow combine this spin polarized band with the light emission. So this is a huge field that a lot of activities there. There are quite a lot of efforts at Harvard as well. So my group, for example, in collaboration with Hong Kong Park's group, also now the Misha Lukin's group also in part of this efforts. We can make this 2D semiconductor, either single layer or bi-layer heterostructures, but also that you can combine that with the transport structures, so you can do the transport measurement. But more importantly, you can also put the gates. And this gate is quite important because the gate can tune carrier density. Also, if it is heterostructures, you can also apply the electric field that just tune these band structures around. Quite preliminary result, we already start to see that the high quality samples, such as tungsten diselenide, when you encapsulate it well, you can get quite sharp spectrums out of it. And spectrum is sharp such that you can actually distinguish which one is excitons, which one is trion, which is basically a charge bind onto the excitons. And there are the trions that can moving around. Also, trion can bound on the surface. There are a lot of structures you can start to see in the optical spectrum. And more importantly, they can be tunable by the gate. Now, you have to be careful. If you have just one gate, gate can dope the sample. So there's a doping, so carrier can be changes. But also, gate can apply the electric field. So you want to distinguish the two effects. And that way, this two gate is quite useful. So if you especially put this top thin gates, such that light can go through, using top and bottom gate, you can either change the density without applying the electric field, or just only apply the electric field without changing density, and that can be done. And we start to see that indeed this two-dimensional excitons, trions, they don't depend on at least their energy do not depend on the electric field we apply, which means that they all reside in the 2D. Basically, their dipole moments are all in the two-dimensional plane, while that their energy can be sensitively depends on these density changes. Not to mention about all this intensity change, which is intriguing things, we know that how to deal with this one experimentally. Now, theoretically also, understanding this the optical and optoelectronic process is a very intriguing process. Already in combination with Rick Keller and Tim Coxeras made quite the progress there. So the last year that you probably heard about Rick's talk discussing about that how do we understand this Raman process in terms of this sliding phonon process. And this is a rather revolutionary the view that really challenging the conventional view of the understanding this Raman spectroscopy in graphene. And they start kind of see that accumulate a lot of this the evidence that actually aligns with the experiments. At this point, probably also, there are more of this also that bilayer photoluminescent with the thermalization. I don't know whether it's thermalization, or is that right?
Well, they say it's thermalization.
Okay.
They say it's nascent.
Okay. So I just kind of reading wrong. Okay. But the important part is this competing view of this, the theories, in some sense, can be resolved by the experiments. And within the center, for example, that Thomas's efforts that kind of revisit some of this Raman process and photoluminescent graphene. Maybe this is good matches, again, just to redesign the experiments to really distinguish between the theoretical description. I think that's kind of quite exciting things to see in the years to come. At the same time also, as I mentioned, that the process of these excitons and trions are quite interesting and also intriguing. We don't understand exactly how this trion and exciton peaks actually moving at this point as a function of the density as well as the electric field. Well, this can be just done again in the collaboration with the theorists. For example, already Rick's group, in combination with the team's group, make the kind of good progress how to understand this the absorption peaks, absorption spectrums by considering this detailed band deformations and the excitons and potentially the trion formations and so on. So I think potentially the theory and experimenters go in hand in hand on this field. It's a newly born field. I believe is a very kind of fruitful field to see. Okay, so that much of the optics. Now, the final topics I want to discuss about the device. Well, remember that our center, the STC, called STC, and S is a science, but what is a T? Yeah, it's technologies, right? It's eventually, we want kind of turn all this interesting physics and chemistries and material science we just do into the devices, right? We have to just demonstrate the technological relevance. So in that regard, this theme is a very important theme, and the project is interesting. Already there are quite of the progress has been made. This is the result from Thomas Palacios in collaboration with Jin Kong at MIT. So in this particular case, they just make the heterostructures between tungsten diselenide and moly disulfide. Moly disulfide is N-type material, tungsten diselenide is P-type material, so this is PN junctions, right? So what's new about that? Well, so you get the PN diode behaviors and so on. But actually they got more. Not only PN diode behavior, so if you just kind of bias right, at some point they also get this so-called negative differential resistance in their the diode characteristics, right? So why NDR? Well, if you just look at the band structures very carefully, if you start kind of bias a lot such that you get the really stiff depletion regime, at some point that you expect actually band-to-band tunneling is happening in this system. So that's band-to-band tunneling is basic ingredient how to create this NDR effect in the typical semiconductors. And that's not surprising to see in the kind of carefully aligned band structures once you make this type of heterostructures. So that's good. So they are seeing this NDR effect in this PN, heavily doped PN junction of the structures. But also they analyze this, the subthreshold slopes of this turning on the conductance, and they start to see that the subthreshold slope is very favorable. It's something like almost 75 millivolt of decades. If you know that electrical engineering, that where the people do care about the subthreshold slope, which actually try to make the fast switch, there's the limits, thermodynamic limits, set by 60 millielectric volt per decade. So it's very close. So which means that at least in semi-classical device, the interface is very good and close to ideal. So that's a good point. One can actually do more things out of this one. So this is a very clever idea. I was really kind of amazed at how they did that. So just using those kind of the NDR effect, which also can be gate tunable, by the way, because that's heavily doped region only that you can see that. And they combine this tungsten diselenide, moly disulfide heterostructures with the regular tungsten diselenide field effect transistors, which actually shows this nice P-type characteristic, while this heterostructure shows this hiccup due to the NDR, right? And ingeniously, they just put them together in series circuits. And that's basically equivalent circuits. So what they do here, basically this is almost complementary, this PN, the complementary CMOS these circuits, except that on this part, it's basically NDR device. At the end of the day, basically what they see that is this circuit has 3 states, not on and off, but there's middle states really stable. So this is basically they call what they call this ternary logic inverter. Basically, rather than you have the 0 and 1, they have the half of the logic. So instead of you dealing with the 2 bits, basically you can just bits. Basically, you can deal with the 3 different states in this type of operation. So that's actually quite good. Already, this device operation can be done only 1 electric volt. That's actually quite intriguing. So this type of the new functional device can be formed, just kind of combine of this type of circuits. So that's an interesting idea. Now, note that this NDR effect is coming from the simple band-to-band tunneling, where you just don't consider the details, but just envelope function type of the density of state arguments, right? However, you can actually push this even further. What if that instead of you have the 2 different materials make the heterostructures, but same material, say tungsten diselenide to tungsten diselenide, right? With this separated with a thin layer of the boron nitride. And of course, you expect some sort of tunneling, but this tunneling is rather different. Now, this is same lattice. Now, if you match the lattice structures well, the tunneling should conserve this momentum conservation in the 2D, right? And that's basically the ingredient. You can make this also the tunneling, but in the resonance. So in this particular device that we can also make this resonance tunneling device, again, just the resonance condition can be tuned by bias voltage and gate voltage. So this NDR coming from resonance tunneling is also controlled by the gate voltage. So that's nice. At this point, the device, the efficiency is really low. NDR only appears like the 1.1 to peak to valley ratio. It's almost like the joke for the real electrical engineers. But at least the first this quantum demonstration of this the resonance device, I was reasonably excited about that. So that's kind of interesting part. And of course, all of this NDR device is very important. I think you see that Tony's face is there. And because electrical engineers do care about the NDR to form the really high frequency circuits. So basically this, the negative part of the differential resistance you can use to construct really fast oscillators and so on. So this fast device, the fast RF device based on the NDR is quite an intriguing part. But you can actually push this idea even further, right? So one thing nice about the two-dimensional system in general is you can actually drive to the system into the really clean limits, right? So here that is a good example. So graphene, once you make the clean limits, and then the transport into graphene in the regional bias can be described by just kind of plasma, the propagations. And Donnie, a few years ago, that Donnie's group just create this, in collaboration with my group, create this, the high-quality graphene device, and they actually demonstrate how this transport, the plasma transport can be measured here. It's also very hard experiments because this can be done only in the high frequencies, and careful the embedding of this, all the parasitic the RF path. But nevertheless, they actually demonstrated this very nicely, the plasma transport in there, and out of that they actually extract information about such as kinetic inductance and collective plasma mass and so on. So that's actually beautifully done. Now, what is the next step? Basically combining this plasmonic or the more importantly, hydrodynamic transport in clean system with fast electronics. So basically that's the next step. So what is the proposal? So proposal is following. Let's imagine that you have the extremely clean two-dimensional system. It's so clean such that elastic scattering or anesthetic scattering length is so long, and basically scattering is strongly dominated by the electron-electron scattering, which can quickly equilibrate, thermally equilibrate. In such a system, I want to describe the electron flow as a hydrodynamics rather than individual electrons. So that's kind of this discussion with hydrodynamics. So then we can think about the following way. Plasmon in such a case is basically the ripples on the top of the liquid that is propagated, right? So think about that I have a pool of these electrons that create the ripples is my plasmon, right? Now I'm just starting driving this the electron system. So I just drive. So my electron pool is moving, right? And then I just create this the ripples on the top, right? And let's watch the following case. So I'm just kind of looking at my electron flow is in that direction. I create the plasma in that direction, right? And then if I just watch from the left frame that how the plasma propagated, of course, that's basically I have to add up these two velocity, plasma velocity with the drift velocity of my electron system, right? So plasma propagates fast, right? However, if the plasma ripple is propagating in opposite direction of your electron flow, of course that the plasma velocity should look like kind of slower, right? This is nothing but just kind of Doppler effects, right? So what you expect to see here is the plasma frequency actually changes over the system. Now, when you actually create this plasma propagation and make the really hard stops and kind of complete reflections of the plasma wave, such that energy that carried by this wave is conserved, right? Because now your frequency got slowed down in this case. Basically, what you have to do is you have to increase the amplitude of this plasma modulation. And this is basically an essential part, how one can get the gain of the plasma, the propagations in the system when you drive in these hydrodynamic regimes. So that's a beautiful idea that Donnie actually figured it out. And the conditions to realize this type of the plasma applications or hydrodynamic application is I need a really high mobility such that I can get the large drift velocity. They will be clear why that's important. And I need a slow plasma velocity. Why is that? Because I want to make this drift velocity get close to plasma velocity, and that's where I get the higher gain, right? Usually plasma velocity is extremely fast because that's basically kind of light coupled with the electron system, right? That's why you need a two-dimensional system, especially gate close by such that you have to slow down the plasma a little bit. And at the same time, you need extremely high mobility, which actually increases the drift velocity quite a bit. What is a system one can use? First, one can use semiconductor heterostructures, and Donnie actually, in collaboration with Amir Yacoub's group, create already this 2D electron empty version of this type of circuits, and they got the preliminary result. Donnie specialist told me that not to show the detail, so I actually shows this data do exist, preliminary data. Don't take the photographs. No, that's okay. You can read this. So data is propagating. Data is generating here now. It's a really exciting field. But of course, same thing can be done in other 2D system. How about it can be in the graphene or bilayer graphene? Again, that using the gate structures, you can also slow down the plasma velocity. Even you can control it very well. And you can imagine that very similar things can be done in 2D system to realize this type of this interesting amplification system. All right, I think that's all that I have. But I'm just kind of trying to summarize a very exciting project that going on in this team. And I'm sure that you are going to hear more of the stories for some of these speakers lines up. But also, from time to time, you will hear from just kind of visiting their labs around. Thank you.
Well, thank you. Questions?
Yeah.
How big are those domain walls in with stacked graphene?
That's a very good question. So we don't have really good understanding at this point. But if they have very similar structures, like in structural soliton found in ABBA domain boundaries in bilayer graphene, it must be order of something like the 10 nanometer. Yeah.
Tunnel through those domain walls?
So apparently that along the domain wall that there is a one-dimensional transport mode along the domain wall. Now if you just look at this across the domain wall, I believe so, because I don't see that there's a gap opens up. Now interesting part is now in principle you can gap it out, the ABBA domain, ABBA vulnerable stack side by applying the electric field. And then how this transport to look like along the domain wall, I think that could be an interesting problem. I don't know, yeah. In principle, yes, right, yeah.
Other?
Yeah.
About that, I think we call it propagating. If you have a tip of AFM or CMP gate.
Yeah.
Well, the advantage is on MS2, it's a semiconductor, so you have a wide bandgap, and I can imagine that you can locally gate it. But when it comes to graphene, I mean, you have very, mobile carriers.
That's right, and that's a very good point. Especially in the graphene, if you just kind of gate it, you cannot deplete it, right? So you can probably create at the most PN boundaries, which is a
solution then, because carriers start to move very fast.
Right. Yeah. So the scattering cross section therefore is probably shallow in the graphene because there is no depletions, and even with the PN junction, there is always Clyde tunneling is happening. So effect must be weaker than in semiconductor system for sure. Yes. Right.
One of your slides, you show eye contact between the metal and your 2D materials.
That's right.
Can you say more detail about these techniques?
Sure, yeah. That's actually published data, so you can find out detail, at least for the graphene. So that's quite early on here. At least in the graphene, so what you have to do is you form the stacks here, and we etch this one. And special this etching formula, I think CF6. I think that some. What is it? What is the best one that we have so far? I know that some of my group members are here, but all gone probably. It's published data. So there's the plasma etching with a specific chemistry. Then you can etch the graphene and boron nitrogen stacks. Usually ends up with a certain angles, about 45 degrees. We hope that we believe that graphene edge is still exposed to edge, and then after that we just deposit the metals on the top in the stacks. Now the first we start with the chrome and some other metals and the following through. And the first metal is very important because they are tend to the metal atoms. The first metal atoms are the one that making the contact, covalent contact onto the graphene, and determine this efficiency of the contact. And seems like the chrome works best for us at this point. One more remark, this method works on the graphene well, but turns out, unfortunately, it does not work too well on other 2D materials. Potentially, their chemistry can be different. So the other 2D materials, there are many different ways of this making contact has been developed. And if you're interested in that, I can just talk to you after the seminar, what is the best that we found so far.
One last question.
About the same topic, so if you remove the barrier and put metal directly on graphene, you have basically both surface contact and the side contact. If I remove that polarized right.
So if we just don't have this one, right?
Yeah. So why it should be better than that? Why here we get?
Well, so when this was first done, that I thought that, yeah, that sounds like the crazy idea. It will not work at all because you're just trying to make the 1D contact, right? So if you just kind of think about contact area, that's basically atomic scale, right? But no, I'm just getting there. But amazingly, this is the best contact one can make compared with just kind of put the metals on the top, even micron size, right? My guess is one important part is here that you basically have the broken chemical bond that can directly make the chemical bonding. While that if you just put on the top, they are still kind of van der Waals, right? Yeah, but when you put it on top, still well, that's experimental finding anyway. Yeah. Yeah. No, that's okay. There's no secret. There's no secret.
Okay, well let's thank Philip.
Thank you.
Next week, Sagar Bhandari from Harvard will be talking about how you NHL electrons through gravity and all of that.
These are great topics. Briefly.
Yeah, and thank you very much. And finally, the students in the course you need to sign up for. So
Sure. So yes, to be fair, there was. when you change the thickness of the metal. So that's another technical problem we are just trying to figure out. Right. But a priori, the good starting point is we just start just looking at the work function of the metal and compare the electron affinity of the optical system and try to match that is a good starting point.
And I'd also like to know how the atomic simulation can help with this. I mean, first of all, I'd like to know, do you know if the contact is ohmic or Schrödinger, how large is the Schrödinger barrier?
Experimentally, we can measure. So if there's a Schrödinger barrier, we can just measure temperature dependence of the barrier. The transport will give us the barrier. If it's ohmic, then the idea is basically linear. So experimentally, in principle, we can just give these numbers. But in past history of all the semiconductor industry, basically the first principle or theoretical calculation to just get this ohmic content has not been too successful. Even for the silicons and so on, this is a horrible problem, right? So I hope that there's a little bit better matches between theory and experiment to the system. But I wouldn't be surprised that experiments and theory can be quite different seeing in the reality. Right. Yeah.
Well, and I know what the problem there. One thing is that in a silicon device, you always have very large screening bag. So if you want to do it as personal, you have to large. The other thing is that you don't calculate the short very accurate.
In a sense, here the screening is even worse, right? Because it's a 2D system, so your dipole layer, whatever form, is not even just infinite plane, it's line, right? So in that regard, the screening is even worse in this case, right? So there are many other things that need to be considered. Yes.
I think that if you recall, intensive interaction with people and we can still work out.
So we have a lot of my students actually work very closely with Capacitance group, so you will find out. So now the semester started, so we will have region probably also joint group meetings between two groups. So you will find out the right people that you can help in my group discuss about this kind of issues.
And do you think that you can determine the atomic structure around this, or no?
Not really. In principle, we can try to